In the previous model, we covered the expectation maximization algorithm for Gaussian mixture model. In this module, we'll talk about the general form of the expectation maximization, which will allow you to train almost any latent variable model you can think of. So it's going to be intense, but going to be worth it in the end. But to start, we will need a few mathematical tools to work with inequalities we're going to derive. So the first tool is connected to concavity and Jensen's inequality. What is a concave function? Well, a concave function f is a function that for any 2 points, a and b, and for any point in between them, it has a property that the value of this point, of the function in this point, the blue point, is greater than or equal to the value of the segment that connects f of a and f of b, so the orange point. Or if you put it more formally, for any 2 points a and b, and for any weight alpha from 0 to 1, if you mix these 2 data points with the weight alpha, you will get a point in between them, and f of this mixture has to be greater than or equal to the mixture of f's. So the blue point has to be greater than or equal to the orange point. Or yet in other words, for any 2 points a and b, the whole segment that connects f of a and f of b should lay below the function f. So if you have a concave function, like logarithm for example, then you can prove the same property but for more points. So for example, for any 3 points and for any 3 weights alpha, which are non-negative and sum up to 1, you can prove that this concave function will, so f of mixture of these 3 points with weights alpha is greater than or equal to the mixture of f's. And you can generalize this thing. You can say that, so first of all, you can call these alphas probabilities, because, why not? They are non-negative, they sum up to 1. So let's say that there is a random variable t, which takes 3 values, a1, a2, and a3, with probabilities alpha. And now we can rewrite this inequality, saying that f of the expected value of t is greater than or equal to the expected value of f of t. It's just the same thing, it's the definition of the expected value. So the average with weights being the probabilities. And this is something called Jensen's inequality, which, if you summarize everything, states that for any concave function f, and for any probabilistic distribution t, p of t, the f of the expected value of t is greater than or equal to the expected value of f of t. And this holds true even if you have 3 points, or if your t takes arbitrarily many points, like infinitely many. And in this case, your summation, your averaging can turn to be an integral, but the inequality still holds. So f of the expected value is greater than or equal to expected value of f for any concave function f. And the final mathematical concept we will need is something called Kullback-Leibler divergence, which is a way to measure difference between 2 probabilistic distributions. So say you have 2 Gaussians. One of them is located at 0 and the other one is located at 1. And both has variance 1. Okay? So how to measure how different these 2 Gaussians are? Well, a natural thing is to measure the distance between their parameters. And it's 1 here, because the variances are the same and the locations are different by 1. Well, it may be a reasonable measure of distance here, why not? But let's consider other 2 Gaussians, which has the same locations, 0 and 1, but they have variances 100. Both of them have variance 100. In this case, the difference between parameters is the same, it's 1. But intuitively, it seems like these 2 Gaussians, the green and the red one, are much closer to each other than the first 2. So, can we build a better way to measure difference between Gaussians, or between any probabilistic distributions? Well, Kullback-Leibler divergence is something which tries to solve this problem. And for example, for these particular distributions, the KL divergence between the first two ones, the blue and the orange Gaussian, will be 0.5, and the KL divergence between the green and red one will be 0.005. So it kind of reflects our intuition that the second set of Gaussians are much closer to each other. So let's look at the definition of the Kullback-Leibler divergence. It may look scary a little bit, but the idea is really simple. So what do I have here? It's an integral of q of x times something, times logarithm of something. Well, integral of q of x is just an expected value of this function. So here we have an expected value of logarithm of the ratio, right? And logarithm of the ratio is trying to measure how different these two distributions are at the current point x in the log scale. So what we have here is basically how different these two distributions are at any data point, at any point of the x-axis in the log scale, and then we're taking an expected value of this quantity. So we're kind of averaging across the whole space, across the whole line, the line of real numbers. And we're getting something like the mean difference between these two distributions. So, again, the definition of the Kullback-Leibler divergence. It has a few properties which we'll use in the following videos. So, first of all, it's non-symmetric, right? If you change p and q, then you'll have different expression. And this is one of the reasons why it's not a proper distance between distributions in the strict mathematical sense. But anyway, it's useful to measure some kind of a distance or difference between distributions. Other property we may need is that for any two distributions that coincide, that are the same, the KL distance between them is 0. And this is really easy to see because if you substitute p with q in the expression above, you will have expected value of logarithm of q divided by q. And q divided by q is 1 at each point. And logarithm of that is 0. So we have an expected value of 0, which is also 0. So Kullback-Leibler divergence between distribution and itself is 0. And finally, the KL divergence is non-negative for any two distributions. And it's kind of easy to prove because you can use minus KL divergence. You can look at the minus KL divergence, which equals to the expected value of the logarithm of the ratio. And we can put minus inside the expected value because expected value is something linear. And finally, we can use the property that the logarithm or minus logarithm of something is the inverse, logarithm of the inverse. And now we have expected value of the logarithm. And as you may know, the logarithm is concave function. It's kind of easy to prove. You can look it up in Wikipedia or just believe me. But anyway, this means that we can apply Jensen's inequality here. And Jensen's inequality will say that expected value of the logarithm is less than or equal to the logarithm of the expected value. And finally, the expected value of p divided by q is just equals to the integral of q times p divided by q, where the q vanishes and integral of p is always 1 for any distribution p, because it's the property of the distribution. And finally, logarithm of this one is 0. So we have just proved that minus KL divergence is always non-positive, which means that KL divergence itself is non-negative. To summarize, KL divergence is some way to compare two distributions with each other. It's non-symmetric. It equals to 0, then we compare the distribution to itself, and it's always non-negative.